עובדים לפני שאנחנו מתחילים? אנחנו לא רואים אותך, כן? אני לא יודע אם תכננת שאנחנו נראה אותך, אנחנו רואים אפור.
רואים עכשיו?
כן.
עכשיו אני רואה, כן.
אמיר, חסכתם לעשות ריסטארט לטימס.
מה חסכתי?
לעשות ריסטארט לטימס.
מעולה.
אפור הזה.
לא, יש עדיין איזשהו ריבוע, זה הריבוע שלנו. בסדר, מעולה, אנחנו רואים, הכל טוב.
כן, אבל אולי כדאי שתזיז אותו, את הריבוע שאתה רואה את המסך, כי הוא מסתיר לנו.
טוב, נתחיל?
כן, בשמחה. רגע. אוקיי.
טוב,
אז
אני אציג אותך. Hello everyone. Today we have a great guest, Omri from Gong, who's going to talk about deep learning and recent advances in this field. Few notes, please mute yourself for this lecture. If you want to ask a question, just use the raise your hand button, and this is it. Omri.
I think we'll
Great.
mute everyone instead, and Omri, unmute yourself.
Yep.
Go.
great. So thank you, everybody. Very happy to be here and to be the comic relief in your conference today. I plan to talk for about like 45-50 minutes, but I'd be very happy if you interrupt me and ask questions and follow with these things during the lecture or afterwards. Maybe just a few words about who I am and why am I here. I head the research department at Gong. I'll share a bit more about what Gong does in a few seconds. And I also teach data science and deep learning at Bar Ilan University and Y Data, data science program. And I come from various backgrounds, but doing research for most of my life. For those of you that don't really get to work with Gong, because Zerto is a long-time customer of Gong, one of the early ones, Gong enables customer-facing people, started with salespeople, but product people, customer success, and others find a lot of use in it as well, to have better visibility into what's going on with the customer interactions. So if all these people are having conversations with different customers, Gong automatically records, transcribes, and analyzes the sales calls, emails, and CRM updates, and takes an hour-long conversation that might look like this and turn it into things like who spoke, when, what was said, the different phases of the conversation, the topics, what happened during the video. So it's much easier to hone in on interesting parts of the conversation. And then we drive this into recommendations. So what do top people do? How can you be better? Should you talk about competitors or not? It's very interesting to see that some people do and some people don't, and there's a lot of just guesswork until you actually see what's working with real data. We develop everything in-house. We have dozens of machine learning and deep learning models running in production, speech recognition, voice print detection, even language detection based on audio, tons of NLP and predictive modeling. And today, what I wanted to do is kind of walk you through the big jump in capabilities that really enable us in Gong to provide something like this, but even everybody nowadays to get to very interesting, very cool projects with not a lot of effort. So when I grew up, the concept of robots was really this. Okay, robots can do dull, repetitive work. This is the only thing they can do. Okay, and this is something a bit different.
So how can I help you? Hi, I'm calling to book a women's haircut for a client. I'm looking for something on May 3rd. Sure, give me 1 second. Mm-hmm. Sure, what time are you looking for around? At 12 p.m. We do not have a 12 p.m. available. The closest we have to that is a 1:15. Do you have anything between 10 a.m. and 12 p.m.? Depending on what service she would like, what service is she looking for? Just a woman's haircut for now.
So, does anybody know why I play that that video? Okay, so this is a demonstration that Google did. It's called Google Duplex, right? It was launched a year ago. A lot of the work was done in Israel. And basically, one of the participants in this conversation is a robot, is a machine. And the nice thing about this is that they did a speech recognition, they did the intent understanding, they did the text generation, and they did text to speech, all of these. And I think that what amazed me when I saw this demonstration is, okay, yeah, they put together things that are that we know can be done for a few years now. And a few years back, like 5 years, and maybe definitely 10 years back, if I'd seen something like that, I would be completely amazed. Here's another demonstration talking about the problems and difficulties with machine learning and artificial intelligence.
We're entering an era in which our enemies can make it look like anyone is saying anything at any point in time, even if they would never say those things. So, for instance, they could have me say things like, I don't know, Killmonger was right, or Ben Carson is in the sunken place, or how about this, simply, President Trump is a total and complete dipshit. Now, you see, I would never say these things, at least not in a public address, but someone else would. Someone like Jordan Peele. This is a dangerous time. Moving forward, we need to be more vigilant with what we trust from the internet. It's a time when we need to rely on trusted news sources.
So I guess that many of you have seen this demonstration as well. This was released, I think, 2.5 years ago. Results right now are much, much better. They work faster. It just looks so real. But what I hope to do in this talk, and I know that I'm going to fail, at least partially, is to teach you how to do those things and explain the concepts behind them, because they're extremely simple in many ways, surprisingly simple. So just a quick history recap. In 2006, Microsoft had a capture project called Asira, where in order to prove that you're human, you had to pick the cats in these images. Okay, there were 12 images. The best computer vision system reached 60% success. So all in all, you had the machine had 0.2% success in completing this. Moving forward to 2014, okay, the best machine learning program reached 99% success on a single image. That meant that basically Microsoft had to retire the Asira project. Do you know why they had a project, by the way? For two main reasons. One is that you could adopt any of these lovely animals, which is a great cause. And the second is that this Microsoft used the annotations that people made in order to improve the models all the time and collect more data. So what's going on? How does this all work? Roughly speaking, in traditional programming, we have the data and we write the program so the computer would be able to generate the output. In machine learning, it's the other way around. We give the computer the data and we give it the output that we want it to generate, and it writes the program itself. Okay, so it's a change in the way that we have the things. How does that work? We show the machine lots of images of cats and dogs. Okay, we feed them into the model each time with the true label. We just show a dog and say this is a dog, and we show an image of a cat and say this is a cat. Okay, we don't do any smart inference like saying a cat has triangular ears, a dog has. all of the other aspects. We just give the machine enough power and enough examples, and it learns to do it on its own. Okay, so how can that actually work? Let's say that we have handwritten digits and we want to label them. Okay, so we have an image 28 by 28 pixels. Let's turn it into a long vector. 784 pixels all in one row, disregard to the information that we have, and connect each of these pixels into one of 10 neurons, into 10 different neurons. Okay, what do we want? We want to feed in the image. We want the network to do some calculation, and eventually the true answer, 8, to have high activation, and all the other neurons to have low activation. And then we'll know that this is an 8. Okay. This borrows a lot from the biological neural network that we all have in our brains. The way that our neural network works is that we have a neuron. The neuron collects inputs from many different other cells. It sums them somehow, and when the input reaches a certain threshold, it fires and propagates the information into other neurons further down in the computation network. Okay, and we can mimic something like this just using mathematical formulas. We take the inputs from all of the different neurons, we sum them, and then we apply some nonlinear activation function on top of them. And based on this would be the activation, the action of this neuron, and again, this neuron and many others would be connected to another neuron in the network. So in our original example, we have all the inputs, we connect them all to all of the outputs, and we have different weights. And this is what the network is supposed to learn, those weights that would provide us eventually with the best solution. So we take all of the neurons at the end. Okay, we normalize them using a mathematical operation called softmax to turn them into probabilities between 0 and 1. And then the network comes with its own prediction. This is green. Okay. This and once we feed it with enough examples, this is a cat, this is a dog, a horse, and this is a dog. Okay, the neural network comes up with some estimation. Okay, and for each of these images, okay, the sum is 1, and this was identified correctly as a cat, but we want it, okay, to be with very high probability cat. So we tell the network, you got it correctly, okay, but let's try to see what you can do in order for your prediction cat not to be 0.71, but to be 0.99, 100. And the same thing for all of the different images. Okay, so we compute the loss. We penalize the network for when it was not exactly correct or wasn't really sure about the prediction. Okay, and we run this through what's called a loss function, a mathematical formula that's very simple, that just looks at the gap between the predicted probability and the true 100% label and collects it. Okay, and each time we feed the network some images, okay, and we see what we can do, how it can change, so that next time it would be a bit better in predicting the true label. Okay, we do this through a process called gradient descent. So in each time, we're not trying to find the optimal solution. We're just saying, what do we need to do? What small change can we do? So we would get slightly better. But we do that many, many times on again and again for days even. And each time the network gets slightly better. Okay, there's a lot of nuances in how to do it well, but basically we start at a point, and each time we see if moving to what side we can improve our loss function and reduce our mistakes each time, and we make a small step in that direction, and after enough time we get to a point where we're happy with the performance. Okay, so basically this is the way that we move across the network, and it learns. And it turns out that this process is very simple. Okay, every time we start with image or some other input data, we run it through the network. We know the true label, we compare it to the network prediction, and then we make small adaptations that can be mathematically derived each step, each time, backwards and backwards in a process called backpropagation. So eventually, okay, all these different weights are learned, and the network knows how to come up with the final prediction. Okay, so this is another demonstration. We show a cat, we show a dog, we show many cats, we show many dogs. Eventually, those different weights are learned, and the network learns how to classify the images. Again, no real feature engineering, no domain knowledge, no need for us to tell the network a cat has whiskers, they're usually in these colors, or all of those things. We just show enough examples. Okay, so traditionally, if we wanted to do something like speech recognition, we had to compute different filters and have a lexicon of the phonemes and do all different recognition steps. And the promise of deep learning is end-to-end learning. Just show us enough examples, tell us what you want our model to generate, and with enough examples and enough computation power, the machine would learn how to do that. Okay. Again, if we're talking about autonomous driving, back in the day, you had to build something that would detect cars and detect pedestrians and plan the path and take all different types of algorithms. And with end-to-end learning, the promise is that you just feed it images and where it should go, and it would learn how to steer the car automatically. So one of the major jumps in the area was because of a data set called ImageNet. This was a shared competition, shared task. It had over 1 million images with 1,000 different classes. And teams around the world were competing to get the best results. You had to make 5 guesses for each image in telling what's in the image. And if any of those 5 top ones was correct, you got it right. It's not always as simple as it looks. There are some examples here. There's another here. And the last one is actually my favorite, this one. Okay, but the cool thing about this approach is that we didn't have to tell anything, to tell the network anything about what's a chihuahua and what's a muffin. It will learn on its own based on enough examples.
Can I ask a question, please?
Sure.
What's the difference between the machine doing this and the human mind? Because it seems like we learn it differently than the way you describe, or slightly differently.
So I'll briefly talk about this. There are some correlations and some that are very different. We know for humans that it's very important to have the guidance. So, you know, just my kid keeps asking me why, and I keep answering or keep pointing at real examples. But as humans, we're much better than just learning from patterns that we see in the world and different aspects. And there are a lot of examples for some preset evolutionary way that things are wired. But for examples, there are experiments done in the 50s of cats that show that if you, I hate saying this, but they forced cats not to move, to tilt their head, and the cats were not able to identify certain orientations of lines, just because the head was always set and they weren't exposed to different orientations, for example. So there are many differences. Some
also
of
have
these things are correlated.
Right?
Yeah,
we have
yeah,
context. I mean, for as a human, the first time you see a cookie, it's on a plate, and when you see a dog, it's outside. You have a lot of additional info that you incorporate into what you learn, which speeds up the process a lot.
Great, and I love the question because we will see how more recently people say, okay, how can we take this context and use it in what we're working? Because coming up with those labels and keep telling the machine, this is a chihuahua, this is a muffin, takes a lot of effort. We need someone to go over this and mark those, and it's definitely not easy. But there's a lot of just information and context that exists in the data itself. Okay, so we'll see how this all translates. So in 2010, the best system had almost 30% errors on the top 5. So even though it gave 5 guesses, in 30% of the cases, none of them was right. In 2012, there was a huge jump in performance, okay? Alex Krzyzewski and other researchers came up with a system that got to 16.4%. Then it got better and better very quickly. And in 2015, the machines actually surpassed human level, okay? So, and they just get better and better at this specific task. Why is it interesting? I mean, how often do we actually just need to look at an image and say if it has a steel drum? So you can see that there are many different categories in the data. Okay, and there are animals, there are different types of animals, and all this information. But it turns out that in order to get better and better, we don't just take the local information, the global information like we did when we took the one vector. We need to take into account the different environment and do something that's very similar to what we have in the human eye and human brain, which is like a neighborhood filters that look at local interactions. And another thing that was found is that if we take deep networks, not just a single layer, but more and more layers, performance gets better and better. And in fact, this was one of the things that people struggle with all the time. Okay, if we look at what was done in 2010 and 2011, it was a shallow machine learning algorithm, no deep network. In 2012, they had 8 networks, and the platform that beat human level had 152 different neural network layers. Okay, so more and more of these get better. And obviously, we had to make a lot of improvements both in the software, but also in the hardware way to do all of those things. So there were very large improvements in the way that we teach the machine to learn, okay, with different techniques. A huge increase following Moore's law in computational power and GPUs. I remember talking to a friend, this is the NVIDIA stock, telling a friend, wow, the NVIDIA stock is going crazy. And he told me, yeah, I made 30% on it. I tell him, how come? He told me, bought it at 10 and sold it at 13. And told him, are you crazy? It's now at 260. So a few years ago, it was very low. Now it's much, much higher. The market is surging. You can see it here. And obviously, the internet and the age of data led us to having much more data. And it turns out that more data is pretty much the best thing you can give to your more quality data is the best thing you can give your network. So what does it actually mean? I mean, you are all engineers, and yeah, we can talk about robots and we can talk about smart stuff, but at the end of the day, we're writing code. So basically, it all comes down to doing this. We start with initial weights of the network, and while we're not happy with the final outcome, we take a batch of data, a batch of images, let's say 100 images, we feed them into the network, we get to the final predictions of the network, we compute the loss, okay? And then we do what's called the backpropagation. Okay, we use the loss to compute how we need to adjust the weights each time. So it will be better and better. And we apply those changes and get another batch of images and do the process over and over again. Okay, and this is an example of a PyTorch code written in Python that actually does that. It's very simple. Nothing much that requires a lot of information. The steps here are basically getting the data, running them through the network. So this applies the neural net onto the inputs and getting the outputs, computing the loss between the outputs and the labels, doing the backpropagation loss. And because these are simple mathematical functions, okay, PyTorch and other deep learning networks know how to do automatic gradient calculations and understand how we need to change the weights in order to make the small step, and you don't have to write all of those things yourself. Take a small step in the weights and continue running. And after 2000 epochs, report the loss outside. And when we do that long enough, we get to very cool results and performance. This is, for example, the definition of a neural network. So this and what I showed earlier is a complete PyTorch code that would allow you to get to very good performance in classifying images. Okay, we have a network, it has a convolutional layer, and then a few linear layers. A linear layer is a layer where each neuron is connected to each neuron in the layer above it. A convolutional layer is a layer where you take the average of your neighborhood and apply a filter to sliding windows across it. But that's it. That's very simple in the way that it rolls. And you're very welcome to play with a demo yourself if you want to get the feeling for how these things work. Let's talk a bit about how this actually correlates with the human brain. So the vision system in humans starts with the eye. In the eye, we have different receptors, and those receptors actually have what's called a retinotopic mapping. What that means is that each receptor in our eye, okay, maps a single angle in space, a single point in space, okay? And this mapping is actually relayed back to our brain. So if you look at the layers, the first layer of the brain in V1, the first visual cortex, okay, there's actually what's called retinotopic mapping on it. And this is the image, for example, that was shown to cats, or in this case, rhesus monkeys. And then they checked the activation of different cells in the cortex, and they saw that there is actually a really a matching mapping. Okay, so this neuron translates to this point, okay, in the world. Okay, but we know that as we go higher and higher up, neurons get from the eye to the V1, and then they move to V2 and V3, and the higher the neurons go, the more abstract and more semantically related information we have in our brain. Okay, until there are some that argue that we have a grandma cell, a cell that fires when we see our own grandma, and only then. How does that translate to neural networks? So we took a network and we trained it to classify dogs, images, sheep, steel drums, and all those things. Then we try to see how different neurons in different layers react to different images. And what we see here is that neurons, each 3x3 square is one neuron. And we check which parts of the images activated the most. So we see that in layer 1, neurons tend to be activated by patches of the same color or by some lines with different orientations. Okay, but bare basic shapes and colors. Slightly above it, we see more complex patterns. Okay, so you see translating lines here or some circles, again, patches of colors, but with some small changes. When we go higher and higher up, we get to things that are a bit more like semantic in the way that translate things. So we have here a neuron that responds to human faces. Different colors, different backgrounds, but these are all like human faces in a way, and not just the faces themselves, but also the torso, the hands, etc. And when we go higher up, we can see neurons that are activated by faces of dogs or keyboards and those lattice-like shapes, many different things. It's very interesting because the only thing we ask the network to do is to tell us if it's a dog, cat, or a sheep. Okay, but in order to learn this, the network learned representations that are useful to extract information that is, very similar to what we see in the human brain as well. Now we do some other experiment, and we take the final activation of the neurons. Okay, and we put two vectors that are close to each other in a 2D grid. Okay, so this image, not in their pixels, but in the way the network understood them, are the most similar, okay, to one another. And then we can see that somehow the network learned that airplanes with different orientations, different airplanes, all of those things are very close to each other. And then, but if they're on the flying, they're more close to each other, then it shifts to airplanes on the ground, and then to other vehicles on the ground. On the other side, okay, we have the airplanes, and then we have ships, probably because of the blue background. And when we have ships, we have other vehicles, and it keeps moving. And somehow, the similarity that was learned between images is useful even for other tasks, not just saying what's in the image, but also learning more properties. And now it starts to get interesting, because if the network learns in different layers, different things, maybe we can use that. So on higher layers, it learns more about the content of what's in the image. On lower layers, it learns about the style. What if we take an image, okay, and we say we want to make sure that the content is very similar to this image, but the style activations make them as similar as possible to a different image. Okay, so this is an example. We take Van Gogh's coffee place in Paris, and we apply it to this video. And what you can see here is that in real time, these things can actually work really well. Okay, the network generates the original image or video content. This is done image by image, but applies to a style change, a neural style transfer. So it's as if it was drawn in the style of a different image. Okay, there are many examples here. I will share the presentation and you can view all these videos yourself. And the interesting thing about this is that we didn't have to do anything different. We just write a network. We tell it that eventually we don't just care about, we don't care if it's a dog, a cat, or a sheep. We just want the image to be very similar to the original content image, but also very similar in style to the style image. And all the differences that we detect are penalized. And the network learns to change the weights slowly with more and more iterations until it gets to a good level. What else can we do? In a completely similar way, we can mark each pixel in an image as a car, a pedestrian, or any other element that we want, and just using the same methodology, pass the image through a network, show it the true labels, and propagate back, and the network learns how to do those things and how to identify the different people and other aspects. Originally, we said, let's try to classify an image as a cat or a dog. What if instead of this, we try to estimate where in X and Y is the location of the elbow, okay, or the hand or the head? If we just give enough examples, enough of these, let's turn each image into just 14 different points. And we have the points. Then the network again can learn how to do this. Each time it will learn the prediction and it will change the weight. So eventually it will get to a good place. If we are able to do this, then we are able to do something like this. Okay, so this is cool and can be done completely with the same methodology that was done before. But if we take something else into account, we can actually do even more cooler things with it. So it turns out that although I showed the similarity between the lower layer and higher layers representation of the network, actually the machine don't really understand the images in the way that we do. Because we can take these images that are classified correctly by the machine, by the neural network, add very small changes to them, come up with these images, okay, which are undiscernible to a human eye, and the machine would classify all of them with over 99% confidence as an ostrich. So obviously there's something that the network learns that isn't really similar to the way we humans do that. But this is part of the game. This is part of what's done. The way they actually do it, okay, and learn how to make those changes is very similar to the approach that was done before. They're actually each time saying not how should we change the weights so that the network will learn that this is a truck or a bus. But how should we change the image so that the system would think this is an ostrich? And it's a very small change in code. And once you do that, the network will tell you how to change the original image so it would be confused. And this was taken to a cool field called GANs, Generative Adversarial Networks. And the concept here is very smart. They're saying, let's have a game between two different networks. The first one, okay, will generate an image, okay, a fake image just from noise. And the second network will get the fake image and a true one. It will need to tell us which one is real and which one is fake. Okay, but it's not the end here, because this discriminator network each time will tell the generator network how to change so it will be better. So it will be more difficult for the discriminator to change. And the generator network eventually will tell the discriminator, oh, you got this one wrong, improve yourself so you would be better at identifying what I'm generating and telling that it's fake. And if we do this cat and mouse game on and on, okay, the generator tries to fool the discriminator tries to find catch the generator, but they're all helping each other get better all the time. When we do this, we can actually get to a level where we can generate very real looking images, because the discriminator is helping the generator come up with things that are more and more realistic and more like the training set. So this is one example for it. Okay, the Irishman as an image took a lot of effort into making, because in part of the video, Robert De Niro and the others appear as the younger version of themselves. And back in the day, this was done by just dotting points on the actor's face so that the computer graphics would be able to map them into different points. But deep learning nowadays is actually, because we had this pose estimation of knowing where the elbows and where the shoulders and head is, automatically does that and automatically maps. And if we put a network on top of those things and try to create better faces each time, we can actually generate new faces. And we have an Israeli pride, the first fake porn, obviously. This cool technology was first taken to porn, where a lot of great technological advances are tried, it turns out. And somebody actually took a porn movie and put Gal Gadot's face on the actress. And the interesting thing here is this is not like a Hollywood studio doing this. This is some guy at the dorm doing this with 1 week of GPU work in code that is published in GitHub and everybody can pretty much do. Okay, and it gets very easy to do those things to a pretty cool level. Another demonstration. Again, we saw that we can take, we do the pose estimation, we're able to get understand what the dancer is doing, and we're able to take two people that don't really know how to dance and create videos that all the time try to fake them. Now you can see that it's not really working perfectly well. When there's a lot of motion, the machine makes mistakes. Okay, it's very easy for us as humans to understand what's going on there, but it's much better than I expected, and it just gets better and better. So this is again from like a year and a half ago. Things nowadays are much better and run much faster. Another demonstration, generating images. This is a work from around like, I think 9 months ago by NVIDIA. So just to show what's going on here, none of these people are real. These are all fake people, and the people in this row are actually what the computer generated when it was asked to blend together the top row and this side image each time. Okay, and again, the way that this was done was just saying, okay, we will eventually feed this image into the network with real images and tell it how are you able to know if this is a real person or not, and with the same time trying to get the network to be very similar to both in style and content to the two images that were created before, with the same automatic gradient computations and backpropagation in the same process. Okay, now this looks very impressive. If you look deeper, you would identify some mistakes, like different color of the eyes, different height of the ears, but generally it looks amazing. I mean, just thinking that the machine would be able to generate this image in such a realistic level is unheard of. I didn't think this would be possible 5 years ago. What about text? Okay, so can we do something like this? Turns out that, yeah, and not really bad. We can take all the Harry Potter books and each time tell the machine, listen, okay, generate a letter, and now we will give you all the text of Harry Potter, and each time we'll show you, okay, the sum of the text, and we'll ask you to predict the next word, sorry, the next letter even, okay? We'll give you the castle grounds now, and you would need to come up with the letter W, okay? And each time we'd run over again and again, and the network learns how to get this better and better. The architecture is similar. It uses a slightly different architecture, but the concept of backpropagation and computation is just the same. When the train starts, it just generates gibberish, okay? But with time, the weights get better and better. It learns to separate things into words. It even learns words that appear a lot, like here or in or on. And after some time, it learns to generate things that do look like Shakespeare plays. This was generated by a machine. This is my favorite, just as readable as any other math text. Now see what it learned, okay? It's quite amazing. It learned that lemmas have numbers and they are sequentially numbered each time, okay? It even learned to generate diagrams, okay? And it learned to start with a proof, and each time, generate something that at least can make sense. And I said, okay, let's put this into a test. Let's go to the Zerto website, take the first 2 paragraphs, I guess that you guys are familiar with them. Let's see what the machine would generate, okay, for Zerto, and see how that competes with what your marketing team is generating. So I'll just read a few sentences out loud. Zerto is a cloud-based enterprise-grade disaster recovery and backup solution that enables organizations to move workloads seamlessly across clouds or data centers. With Zerto, a wall of true interruptible technology is within reach. Again, none of this was taken from the internet or whatever. It just got these 2 paragraphs, learned that the world, the context, the domain is around these things, and then try to see what's most probable when we're trying to generate text in the way that I mentioned it before. Okay, what else can we do?
I have a question.
Sure.
Every technology that you've shown here, it's like a different bot, right? It's not the same bot that can do all these things all together. I mean, there is a bot that can manipulate text, and there is a bot that can manipulate pictures, and there is a bot that can manipulate videos, as is shown before. So each of these examples that you gave are different bots. Am I right?
So yes,
there is no one bot that can do all of this.
Yes and no, okay, because the framework underneath, the infrastructure, the way of operation, the method of operation of doing those feed forward and back propagation, small changes, and these things are all the same. You use the same technology to achieve those, okay? A lot of the time, what you actually do is you take the network. When you do the style transfer, you take the network that was trained to classify dogs and images and dogs and cats, and you use the same network that was trained on a different task for your own task. Okay, so let's see an example for that, and that's interesting. We've seen that we can take an image and classify that it has giraffes, and we've seen that we can even, you know, take the style of it and whatever. Let's take the image and put it through one of these pre-trained networks and get a vector, the finite vector that I use to show that planes are closer to each other, and then there are ships, etc. And then take this vector and map it into text, because we know how to generate text, right? Okay, and if we give it enough examples of images with the text that they have, we can come up with things like this. We show the machine an image, and it tells us that this has man in black shirt playing guitar. Okay, and this is incredible to me, like when you see this, but when you understand the concept, it's just the same. It already learned how to generate sentences. It learned to understand what's in an image, and now we teach it to connect those two things together with a large data sets of images and sentences that match them. Okay, these are more examples. The girl in pink dress is jumping in air. Okay, the network doesn't know that this is a girl and this is a dress, and doesn't understand these concepts per se. Okay, but it learns to generate those things, and I find it amazing. What else can we do? Okay, we've seen before that we can identify people and we can identify cars within images. Let's use the same technology to find points of interest, and for each of them generate text. Okay, so in this image, okay, we see that we have a ball that is white, the ground is visible and brown, there's an elephant standing, there's a shadow on the ground, and all of those different aspects. And the machine can generate all of them. Okay, now this is a game changer for blind people, for example. If you're able to just build an app that just activates a camera and talks about what it sees, and gets better and better with more data and annotations. We can even teach the machines.
Can I have another question, please?
Was there a question? Sure.
Yes. What is the limitation? I mean, where do you tell the machine that this is the only thing you need to learn? I mean, it's like when I'm thinking of it, it's like the apocalypse of the machines. When you think of it, like, where is the limitation? When you tell the machine that's here you stop and you don't try to learn more into this, or to figure more into this.
So we will get to this in a couple of minutes.
Yeah, thanks.
Okay. Another thing when you're doing translation is that you can ask the machine to tell us and even use the information of what it cares most about when it made a prediction. So if we take a French sentence and an English one, we can actually see the network tells us when although the order is not the same, okay, when I had the word zone in French, I translated it into area, and I changed the order of those things, even though we didn't ask it to translate each word separately. We just fed it with an input sentence and the output sentence, and we gave enough of these, and the machine learned how to do that. So here's another example of what you can do with this technology. I find it quite amazing, but this is a designer, okay, that is big into code. He's not a deep learning researcher or anything like that. And what he's done is just take an image, understand what's the main object, separate the background from the image. We've seen before that we can identify humans, we can identify cars, the same technology, just separating the background from the foreground. And then he crops it, and he moves the cell phone into the computer, and with augmented reality is able to understand the exact location. This is an image. Once he cropped it out, this is an image, and he puts it into the website that he designs. Okay, just tying together elements that are not very complex. The code is on GitHub, and it's quite amazing how you can do those things. We're short on time, so maybe I'll jump this, but I think that in many cases, this is something that you can try, and with some cases get a good success in. One example from Gong, during these conversations, it was interesting for us to say what's more useful. Should you just use the webcam to have a close connection Or should you show a presentation or do a browser demo or something like that? And we needed to classify these. And all we needed to do was to take 5,000 images. It takes around like 4 hours to for a student to label them. Okay, take one of those networks that was trained on ImageNet to identify cats and dogs. Okay, take the network and what it the final vector and just change slightly the weights in a very easy manner, so that it learns to match not the 1,000 categories of ImageNet, but the 4 that we had. Okay, so this is answering the question that was asked earlier. What's different and what's similar between these networks? So we actually took a network with the architecture and weights that was used for this, and we used it with its weights and aspect to our own problem. And it was done in, because the network also learns all the important aspects of this. All we needed to do is just follow this guide, put our different documents in different folders, and run this single line of code. The network learned, we got a model, we saved the model, we were able to push it in production, less than 1 week of work for a very cool machine learning, deep learning feature. Okay. Another cool thing that we see here, and it translates to what we've seen before, is that the machine is able to identify presentations, although they are very different from each other. The fonts, the outline, the colors, all of those things are different, but these are all presentations with high confidence. And when it wasn't really sure, it made sense. Okay, this is just a website, but the image here is kind of confusing. Maybe it's a presentation. This is a presentation given inside a browser. So it wasn't really sure, is it a browser tab or a presentation? So we can see that the machine is even making intelligent mistakes when it's working. Now, how does this translate? What's the end game? Is it really that the robots are coming and resistance is futile? Media likes to say that, and they keep pushing those things. If you actually look at examples and see the code, you know that it's very difficult to get those things. In papers, they show the successful examples. So this is one of my favorites: a baby laying on the bed with a stuffed bear, or a woman holding a teddy bear in front of a mirror. Okay, there are other examples that I can share. I feel that we're very far from real intelligence. I mean, when the machine would just not tell us this is a dog, this is a cat, but tell us you're fat, this place is boring, and I really hate chess, we know that we made a good progress. But honestly, with the way the progress of things, it's quite amazing, and I don't know where things will go. We do see trends of people putting more data and more computational powers, and with distributed computing, it goes crazy, because companies like NVIDIA or Google, Microsoft, and Salesforce spend it gets to close to $1 million to train one very large model. But the cool thing about this is that when you have the model, it's not just for one task. You're able to do many different things with it, and it's useful for many different tasks. So it still remains to be seen what you do with all of the data and all of those machines. But it takes a lot of work to actually make sure that things work, and a lot of thinking to solve all of those problems. Personally, I do see the change. I mean, you can see how kids are much more accustomed to living with technology, living with robots. They feel much more confident about those things. I have 2 daughters, and when my youngest one was born, the eldest wanted to put her into the youngest bed. There was a mobile playing some music, and then she just said, "Okay, Google, stop." Because this is how she's used to us stopping the music at home. So so for kids and for others, it makes much more sense that, yeah, technology would be able to do those things, achieve them, and get to cool results. And I think that part of what we're trying to do is just maybe, okay, try to help this revolution, but seriously in good ways. It's very easy to take those things to bad places. History is full of examples of people trying to stop progress and stop technology. It never worked, really. And I think that there's a lot more good that can be done than harm, but it really requires us to, you know, not be tempted for the quick gains and the easy money, and actually say, wow, we can really make a contribution here and work on things that are very useful and important. Hopefully this was interesting. If you are interested in learning more, as I've said, I teach at the Y Data program. There are a lot of classes over there that around data science, machine learning, and deep learning. And many of the projects that were shown here, we actually have as part of the course. So if anybody is interested, you can go to the website and even type the coupon code for a discount. And I don't know how much time we have. Sorry for taking up so much of your time, but very happy to answer questions.
1 minute actually.
Cool. So one question.
One question, guys. The pressure is too high.
Just
cool. So
it was a really interesting presentation, and thank you.
Great. Thank you, everybody. Happy to stay in touch. If you have follow-up questions, it would be my pleasure.
Thank you.
Have a great day.
Thank you.
Well done. Thank you.